Okay, this will be a review of the material we took in weeks 6 through 8. All right, we'll start off with some questions that require us to use Bayes' theorem. I'll read it. We have company A, and some are defective. Company B, another 2% are defective. And then given that we do pick a defective range, we need to find the probability that it came from company B. My advice for all of these, because we're given a lot of information, is you actually want to start with the question. So the question says, given that the range is defective, so probability, given that something is defective, that it came from company B. So Bayes' theorem tells us that this probability can be written as follows. You'd find the probability of B only and the probability that it's defective only, and we multiply it by this reverse contingency, so the reverse of these two, which is the probability that is defective given that it came from company B. Now, the top two are quite easy, and the bottom one will take a little bit more to calculate. But now let's go ahead and read from the top of the question. Company A, there's 500 ranges. So the probability that we came from company A is, remember, there's 500 ranges, and there's 850 from company B. So the total number of ranges, 500 from company A, 850 from company B, that's 1350 total. And probability that came from company A would be 500 out of 1350 total. The probability that we came from company B is 850 out of 1350 total. Then let's continue to read. The probability that it's defective if it came from company A is 2%. So the probability of defective given that it's company A is 2%. And the probability that it's defective given that it was company B, also 2%. That's not always the case that it's the same number. Okay, now we have all the information we need, and let me go back over here to our formula. The probability of coming from company B, the probability that it's defective from company B, those are numbers that we now have and we can plug in. The probability that it is defective, that's something we don't have. But actually, we can rewrite this in this way. If we want to know the total probability of the item being defective, it's either defective and it came from A, so we do the probability of A, and that it's defective and came from A, or, so we do plus, the probability it came from B, and, remember, and in math we multiply, the probability that it's defective and came from B. So now we can go ahead, we have all these values. So we'll say 850 over 1350 times 0.02 is the top. And then the bottom will have 500 over 1350 times 0.02, the probability it's defective and came from A. Probability it came from B is 850 over 1350, and the probability it's defective and came from B is 0.02 in this case. And we'll get a final answer that the probability that if given the range is defective that it came from company B is 17 over 180, which we can simplify as being approximately 9.4%. Okay, let's try another one. We've got a corporation. It has 3 methods this time of training its employees. And we've got location A, location B, location C, and different success rates at each location. In general, I would advise go to the bottom of the question and read what they're asking, and that will help us set up everything else. So it said, if a person passed the exam, so they're saying, look, what is the probability that given that you passed the exam, that you came from location B? So again, according to Bayes' theorem, we'll say that's the probability, the overall probability of coming from location B divided by the overall probability that you pass the exam. And here on top, we do the reverse contingency times the probability that if you came from location B, you passed the exam. So now we can start reading at the top to see all the information we need. It says 20% of employees go to location A. So the probability that the employee went to location A is 0.20. 35% to location B. So the probability of going to location B, 0.35. And the probability of location C is 45%. All right, and location A has an 80% success rate. So what this means is the probability that you succeed given you went to location A is 80%. And we'll keep reading. Okay, location B has 75%. So the probability of succeeding given that you went to location B is 75%, and location C is 60%. So the probability of succeeding given that you went to location C is 60%. And you know what? Over here I wrote pass instead of succeed. We'll change this to the letter S for succeed. Succeed meaning pass. So the probability of success. Just so we're consistent and we don't get confused. So when we look at what we have the probability of B, we have the probability of success given that we went to location B. Now we need the overall probability of success, which we don't yet have. Which, by the way, what you do, so the top will remain the way it is because this is things we can just plug in a moment. The bottom, the probability of success. When we don't have that overall probability, we can do it piece by piece. So we can say, well, if you went to factory A, that's the probability of A times the probability of success at A. Or you went to B, so the probability of going to B times the probability of success at B. And then lastly, the probability you went to C times the probability of success at C. Okay, we actually have all of those numbers. So now we'll go ahead and plug them in. And after we plug all that in, we get the probability that if you succeeded, you came from location B is 105 over 277, which is approximately, 37.9%. Okay, now let's move to questions about probability distribution. So this question gives us a table of values, and it says for the different number of backups, successful backups completed daily for different clients, we have probabilities. So 50 backups completed, that's a probability of 10%, 100 backups, 20%, and so forth. So here we have the table. First thing it asks us is to verify that it's valid. Now, to verify that a probability distribution is valid, all you must do is add up the different probabilities and make sure that they add up to 1 or 100%. So when you add those all up, yes, in fact, they do add up to 1.0, which is 100%, which means yes, it is valid. It is a valid probability distribution. Okay, now to calculate the mean, I'm going to look at all these questions. The mean, the variance, and the standard deviation from this table, we're going to have to make a few more columns in the table. So first of all, I'm going to rewrite this table going vertically downward. So there it is. The first thing we must do to calculate the mean is we'll make a new column, which is x times p of x. Okay, so we'll multiply going straight across. 50 times 0.1 is 5. 100 times 0.2 is 20. 150 times 0.4 is 60. 200 times 0.2 is 40. And 250 times 0.1 is 25. Now for the mean, all you must do is add up this column. So we'll do the sum of x, p of x, which, by the way, equals the mean. And so what we get in this case is the mean is 150. So we've answered the mean question. Now we will move on, and they're asking for the variance and the standard deviation. So in order to do that from this table, we're going to need a column called x squared. And then after that, we will need a column x squared, p of x. So let's do that, and then I'll tell you what we must do from there. So when we say x squared, it just means take the x and square it. So 50 squared is 2,500. 100 squared is 10,000. 150 squared is 22,500. 200 squared is 40,000. And lastly, 250 squared is 62,500. Okay, and for this last column, we'll take that x squared number, this one, and we will multiply it by p of x. So 2,500 times 0.1 is 250. 10,000 times 0.2 is 2,000. 22,500 times 0.4 is 9,000. 40,000 times 0.2 is 8,000. And lastly, 62,500 times 0.1 is 6,250. We're not done yet. Now, what we must do is we're going to add up this column, the sum of x squared times p of x. So we will add up all these numbers, and we get 25,500. Now, if we want to find out the exact value of the variance, the rule for the variance, it's called sigma squared, and it's this summation that we just found minus the mean squared. So it's 25,500 minus 150 squared, and we will get that the variance, which is equal to sigma squared, is 3,000. Lastly, it's one more simple step just to find the standard deviation. And the standard deviation, you just take the square root of the variance, so it's just sigma, so it's going to be the square root of 3,000, and we will get, let's see, approximately 54.8 equals the standard deviation. Okay, now I want to talk about a special kind of probability distribution. It's called a binomial distribution. And what makes that special is that the probabilities are taking into account something that only has basically two outcomes. This is what the prefix by means. So for example here, we said the probability of a student passing is 65%, which basically means the probability they don't pass is 35%. And when you have a binomial distribution, which they're saying we have, there's special shortcut ways to find the mean and the variance from the data itself. So let's go ahead and we will answer some of these questions. What's the probability that exactly 4 students pass the retake? So this is the probability of 4 students. So exactly 4 students pass the retake. We would say the probability is 0. Exactly, we'd say 317,313. If I were going to approximate, I'd say approximately 31.7% is the probability that exactly 4 students pass the retake. When they say, let me go ahead and erase this, when they say the probability that at most 5 students pass the retake, okay, that means it's the probability of 0, 1, 2, 3, 4, or 5 students passing the retake At most 5, so meaning we really don't want 6 people. That would not be success in terms of this question. So you could do the probability of 0 plus the probability of 1 all the way up to the probability of 5. You could do that. I'm going to do a little shortcut method and say, look, the probability of at most 5 is actually going to be the same as 1 minus the probability of 6, because 6 is not what we want. We want the others. So it's going to just be a shortcut calculation. We have 1.0 minus the probability of 6, 0.093533. When I do that calculation, I'll get 0.90647. And by the way, if you chose to do it this way by adding up all of these probabilities, you should get the exact same answer. So the probability at most 5 students pass the exam, that just means not 6 students passing, is going to be approximately 90.6% probability. Okay, let's look at question C. What is the probability that no student passes the retake? Well, that's the probability that 0 students pass. So again, we can none pass. That's just the probability of 0 students passing, which is directly given 0.0025, which is approximately, even if we changed it to a percent, it's quite small, 0.25%. So a quarter of 1%. Very unlikely that none of the students pass. So now we get to the meat of the question, which is kind of a shortcut way for calculating mean and the variance. When we have a binomial distribution, we won't need to make all those extra columns like we did in the previous question. And it turns out that you can find the mean when you have a binomial distribution. It can be found if you just know the n, which is the number of trials, the number of opportunities for success and failure, times p, which is the probability of what we consider success in our specific experiment. So in this experiment, they're saying, look, n equals 6, and the probability of success, which is passing, is 65%. And therefore, we can just plug those numbers in, 6 times 0.65, and that calculation alone will give us the mean. So in this case, we get that the mean is 3.9. So on average, if I have 6 students that I'm allowing a retake, on average, I would expect that 3.9 of them will pass. So close to 4 students will pass is what I would expect on average if I repeated this experiment over and over and over again. So secondly, they are asking for the variance. Variance, again, we call sigma squared. And it turns out also we don't need all these extra columns in the table. We can shortcut it when it's a binomial experiment. We need one more piece of information though. Beside needing P, we'll need something called Q, which is the probability of failure. So that's actually just 1 minus P. So in this case, 1 minus 0.65. And so we'll get Q is 0.35. And now the formula is the variance of a binomial experiment is just n times p times q. So I'll plug in those numbers, 6 times a 65% chance of success and a 35% chance of failure, and we will get, I'm running out of room, so let me write it over here, we'll get that the variance is 1.365 in this case. Okay, the last thing I want to talk about is tree diagrams, and this is something we didn't spend too much time on, so I wanted to make sure I cover it in a video. And, well, let's just read the question. It says you have a set of 15 playing cards, 6 of them are red and the rest are black. Well, let's stop right there for a minute. So, the probability of picking a red card, let's just think about that. If 6 of them are red, out of a total of 15, that gives us the probability of picking a red card. And it says the rest are black. So the probability of picking a black card is, if 6 are red, 15 minus 6 are black. 15 minus 6 equals 9. Okay, so we've got 9 out of 15 is the probability of picking a black card. Okay, fair enough. It says you choose a card, then you place it back in the set, and then choose another card. So we're choosing 2 cards total, but these choices are independent, meaning the second time I pick, it's the same probabilities as the first time I picked. Why? Because I'm sticking the card back in the deck, and the second time I pick, it's the same deck of cards I'm choosing from. So often we can visualize this using a tree diagram. What do I mean? I mean, we look at, okay, we'll put the first pick, and then we'll put the second pick as like a branch of the tree. What do I mean? I mean, okay, the first pick, I either choose a red or a black card. Second pick, because I replaced the card back in, I still have the option. I can either choose a red or a black card. And here, I either choose a red or a black card. So in fact, all the options, let's look at all of them. You can pick red followed by red, red followed by black, black first followed by red, and then black first followed by black. Now all of these different outcomes, these 4 options, will have different probabilities. And here's how we calculate them. So first we say, look, the probability of red is 6 out of 15. The probability of black is 9 out of 15. Moving along, the second pick, those probabilities don't change. Why? Because we put the card back in the deck, meaning we have that same deck to choose from. So probability of red is 6 out of 15. Black is 9 out of 15. Here, red, we've got 6 out of 15. And black is 9 out of 15. And so if we want to know the total probability of picking a red followed by a red, we would just multiply these probabilities. 6 out of 15 times 6 out of 15, which when you multiply that, you get 4 out of 25, which is 16%. Okay, and then we can do the next option, which is first choosing a red and then a black. So that would be 6 out of 15 times 9 out of 15, which will simplify to be 6 out of 25, which is 24%. So 24% of the time we would have that outcome where we chose a red and then a black. Okay, let's look at this third outcome, black followed by a red. So black, the probability was 9 out of 15, and then the red was 6 out of 15. Okay, so when we multiply that straight across, we also get 6 out of 25, which is 24% probability. And then lastly, if we were going to choose a black card followed by another black card, that's 9 out of 15 times 9 out of 15, which ends up being 9 out of 25, which is 36% probability. Okay, so that's the idea of using a tree diagram to calculate the probabilities of the different options. Okay, I hope this helps. Thank you.